We just calculated the maximum number of modules we can have in series. Let's go ahead and look at the math for determining how few we can have in series, the minimum number. Got to consider the fact that we're talking about hot modules in the sun. Has a huge impact on the minimum number of modules in series. The minimum module voltage is going to occur during the hottest time of the day, and it's occurring while it's operating. So we're going to be basing this calculation on VMP, not VOC, like we did for the maximum number in series. Also have to realize that PV modules in the sun are hotter than the ambient temperature. Not really a newsflash here. Something that's dark blue or black sitting in full sun, it's going to get pretty warm. You put your hand on it, you can tell that it's hotter than the ambient temperature. And we're concerned with cell temperatures here. So the fact that the module's hotter than the ambient temperature means the ambient temperature alone is not suitable for determining how low voltage is going to go. We're going to underestimate how low it's going to go if we don't take into account the fact that, yeah, these modules are way hotter than the high temperature that we're using. So very important. So what we do is we use something we call a temperature adder, or TAD, if you will. This is going to be added to the ambient temperature to reflect that very fact that the modules are hotter than the ambient temperature. And there's been a lot of research that's gone into this. There's been a lot of data gathered over the last decade or so, and it's going to vary by season. But we don't really care about season, right? We're worried about summer when it's hottest. It's going to vary by mounting type. Well, that's pretty easy to deal with. We can kind of have some generic temperature adders based on the mounting configuration. You can imagine a pole mount versus a ground mount versus a flush roof mount, different air circulation around those, different convective cooling amounts. So there'll be a little bit of a difference. In general, a 30 degrees Celsius adder to whatever that high temperature is recommended for rooftop systems. Ground mounted systems, about 25 degrees Celsius. And then for pole mounts, which tend to have the most convective airflow over them, a 20 degrees Celsius adder to the ambient high temperature is what we recommend. So we're going to use, when we do our calculation, again, we're going to be seeing how much does voltage change relative to the temperature. In this case, we're using VMP as our voltage. We need to use a temperature coefficient that corresponds to that. Usually, you cannot find the temperature coefficient of VMP. Not usually given with most modules that are out there. But we are always going to be able to find the temperature coefficient of maximum power, TKPMP. Going to find that for all modules. How much does output wattage change with temperature? Well, we know that the effects of temperature, while not limited to voltage, are primarily on voltage. It has a dramatic effect on voltage, the change in temperature, like about 1/3% for VOC. And the effect on short circuit current or current is very minimal. It's very minimal. Oh, so minimal that we don't even really worry about it for the most part. It's almost zero. So we can effectively say that the temperature coefficient of maximum power is a suitable proxy for the temperature coefficient of VMP. Is it 100% right on? No, but it's really going to be close enough in nearly all cases. So yeah, it's hard to find that TKVMP. You can kind of derive it if you want to. But the change in voltage is really what's driving things here. And that's also what we're really concerned about because we're talking about voltage. How few can I have in series and still provide enough voltage to this inverter? Other things we want to think about, as I briefly mentioned already, voltage degradation and other losses. We're losing voltage because of heat. What other things are happening in the system that's going to cause us to lose voltage? In order to take that into account, what we normally do is we shoot for 110 to 120% of the inverter minimum. So if it's a minimum of 400 volts, I'm going to shoot for 440 or 480. 110 or 120% of that in order to account for the fact that 10 or 12 years down the road, we're going to have less voltage from my module. I've already got a percent of voltage drop or whatever it is in the conductors running back to the inverter anyway. So this kind of gives us that slop, if you will, or that buffer so that over time we don't get down to 100%. If I design and install a system on day one and I've calculated that the minimum module voltage is equal to the minimum input of the inverter, well, it's going to be below it 5 years down the road. So we don't want to shoot for that. We want to shoot for a buffer, 110 to 120%. Part of this is how we account for that power degradation. You can think, it's going to happen. Look at how module warranties are structured. They assume a power loss over time. And it can vary by module. But in general, around 1% degradation per year is a commonly used factor. And we could say that, okay, half of that is current, half of that is voltage. So 0.5% voltage loss per year. These are ballpark numbers. Some modules are probably better, some are probably worse, but these at least give us a target to shoot for. We also want to think about that DC voltage drop, as I said. Module voltage variation is another one. We kind of think that, hey, my module's got a label on it, that's what it makes. No, if you look at the fine print, there's a window there. That voltage or current rating of that module may be plus or minus 5 or even 10%, even if they have the same power rating. And they just have slightly different voltages and currents to get there, and that's just inherent in the manufacturing and binning process. So we might have some low voltage modules, even though they give us the watts they're supposed to, right out of the box. Let's use this multiplier to kind of take that into account. We don't want to operate at the low end of the inverter voltage window either, because as I said, if you do that early on in the system life, over time, you might be below it. So want to take that into account, that the array voltage may drop out of the window over time. Here's the calculation. Again, we're going to calculate a temperature-corrected voltage, a minimum voltage, for a single module. We're going to be using the VMP. We're going to start with 100% of that. We're going to figure out what our temperature difference is and how much change we get with the temperature coefficient based on that temperature difference. Let's go through the math. So 36.8, that's our rated VMP off the module spec sheet. We start off with 100% of that. We're going to add to this, probably going to be subtracting in the end, as I bet you get, as you can imagine, our temperature adder, 30 degrees Celsius in this case for our roof-mounted system. Our high temperature, this is our ASHRAE 2% high, of 41 degrees Celsius. And then we're going to subtract off the starting point, STC temperature of 25 degrees Celsius. Whatever that temperature change is, that difference from standard test conditions, multiply it by temperature coefficient of maximum power, 0.41% per degree Celsius, and then we'll figure out what our change is. So we do the math here. We see that we have an overall temperature change of 46 degrees C above the standard test condition temperature. So higher temperature, voltage going down. That's the whole idea here with minimum modules in series. So if you add those temperatures up, we get a 46 degrees C difference, multiply that by 0.41% change for each one of those degrees Celsius, and we see now we're doing a positive temperature times a negative temperature coefficient. We end up losing 18.86% of our voltage. So we're actually going to subtract that off of the 100% we started with. We'll change them into decimals first. So 1 minus 0.1886. And we end up getting 81.14% or 0.8114 of the VMP we started out with. So we'll take that 36.8, multiply it by our 0.8114, and we determine that our temperature-corrected minimum module VMP is just under 30 volts, 29.86 to be precise. As I said, we're going to be shooting for 110 to 120% of the inverter DC voltage input minimum. So we've got the ideal 120%, we've got the okay 110%. Often you come out somewhere in between or closer to one than the other. Let's go ahead and see how it works out in this situation. So the ideal world, 120% of that minimum, we're going to take the inverter rated minimum, 450, multiply it by 1.2, that's our 120%, and then divide by that temperature corrected minimum module voltage that we just calculated, 29.86. So 540 volts is what we're really shooting for. Divided by 29.86 says greater than or equal to 18.1. If we round down, well, now we're going to not have enough. So we want to round up to 19. So 18.1 gets rounded up in this case to 19 modules, which is what? The same number as the maximum. The same number as the maximum. So what are our choices? 19 or 19? I hope you like 19. Okay, that's ideal. What about okay? What about an okay world where we're only taking 110% of that input minimum? 110%. Well, we see that we are going to, in this case, be targeting 495 volts divided by that same temperature corrected module minimum voltage of 29.86. 16.6, we're rounding up, tells us that we need 17 in series. So 17, 19, we got two different values for the minimum here. Again, real world, what is this actually going to pencil out to? We just rounded up from 16.6 to 17. Right? So 17 times 29.86 is going to be more than 495. So we have a little buffer built in. Our actual percentage of the inverter minimum is going to be maybe like 113%. You can do the math and figure it out. Anyway, we've determined that we have some options. 19 is our maximum modules in series. It was also our minimum in series in an ideal world. However, we also saw that we could really probably get away with a minimum of 17 in series. And what does that also mean? Well, of course, it means that 18 in series is also an option. So 17, 18, 19. 3 different string lengths possibilities for connecting modules to this inverter in these conditions. Up next, we're going to talk about inverter input limits and DC to AC ratios as we can continue on matching PV source circuits to inverters. Talk to you soon.